Hello, linear algebra student. This video is for chapter 5.1, Eigenvectors and Eigenvalues. So what is this about? Let's talk about these new terms. Eigenvector first. Eigenvector is a non-zero column vector like x1, x2, x3, xn, all the way to xn if we have Rn. That corresponds to the input for a transformation. So you have a transformation AX, a linear transformation, so it has a corresponding standard matrix. So X is Rn. So this particular vector is very special. When you go with the vector, the answer is a multiple of X. Usually after you do AX, you would have another vector, right? Anything like AX equal to B is totally different from X. But what happened is your answer of this multiplication become a multiple of X. And this scalar is called lambda, which is a Greek letter spelled as Lambda. So this scalar is called because it's related to associated with X, we call it the eigenvalue of A. If you can solve AX such that AX equal to lambda X. So they go with a pair. So a particular lambda is associated with a particular eigenvector. So this is eigenvalue. This is called the eigenvector, such that A times the X would equal to lambda X. Because it's a transformation, so we assume A is a n times n matrix. Otherwise, you would have different. So A is a n times n matrix. Otherwise, your B would not be lambda x, right? B would have the same, would be m row, right? So you can understand this from a transformation perspective is if t of x equal to ax equal to lambda x, that means after your transformation, your x originally is this. Now it become a multiple of it. It's longer or the other way around or the other direction. So it's just so it travel on the same line, but just become a multiples of the original vector. And from an equation perspective, it just means that ax equal to lambda x has a non-trivial solution. Of course, x equal to 0 is always a solution. And this vector x has to be a non-zero vector. So this equation ax equal to lambda x has a non-trivial solution. So let's check how to figure out if a particular vector is an eigenvector first. So I have a transformation A is 2, 3, 5, 4, and I want to check if U and V are eigenvectors. What's the definition of eigenvector? Eigenvector means AX is equal to a scalar multiple lambda of X, right? So I'm just multiply it first to let U go through the transformation. So that's just multiplication, row times column. So it'll be 4 plus 12. Row times first column will be 10 plus 16. You can also use a calculator to do, but this is a 2 by 2. It's easy to do. So 26. Is it equal to a multiple of 2, 4? No, you cannot factor a multiple of 2, 4 out. You factor 8 out, then this is not 32. So we say 2, 4. So we say no, 2, 4 is not an eigenvector. It's just a input is in the domain of the transformation, but it does not create it is not the eigenvector. What about 3, 5? So if I do row times column, it will be 6 plus 15. Row times column, 15 plus 20, right? So that would equal to 21, 35. Oh, if I factor 7 out, I would have 3, 5. And this is actually lambda of V, right? V is 3, 5. Now I have 7V. So yes, 3, 5 is an eigenvector. So it's very easy to check if something is an eigenvector. You just have it undergone the transformation to see if it become a multiple of it. The second, following this, we're going to talk about if someone tells you an eigenvalue. Okay, we'll talk about how can you figure out that eigenvalue. So this is the beginning. So suppose I tell you that, oh, I did for a particular A, I know an eigenvalue. Find the eigenvector because they goes in pairs, right? So just like before, 7 and 3, 5, actually a pair of the eigenvalue and eigenvector. So if I tell you 7, how can I figure out the eigenvector is 3, 5? So let's look at this equation. So this is a definition of eigenvalue and eigenvector. So ax equal to lambda x. It has to satisfy this. So from a equations perspective, lambda x can be written as I times x, right? I times anything is just the same thing. So I can write minus lambda x on this side. I can write the equation as ax minus lambda ix equal to 0. Remember, lambda is given. This is not an unknown. The unknown is x. And then I factor lambda I as a identity with the multiple of lambda. And then I factor a minus lambda I out, x equal to 0. So this has become a new equation. It is a homogeneous equation. And so because lambda is a eigenvalue, this should have a non-trivial solution. And the solution is the eigenvector. X is the eigenvector. If I solve this equation, eigenvector. So basically, to find the eigenvector, you are to solve this equation. This is a homogeneous equation. So, summarize. If to check if x is an eigenvector, check multiply a with x to check if it's a multiple of x. To find an to check lambda is an eigenvalue, solve a minus lambda I x equal to 0 by finding RREF of the augmented matrix of a minus lambda I and then 0 to see that it has a non-trivial solution. And if you actually want to find the corresponding eigenvector for this eigenvalue, you will actually solve it. Okay, so we will actually do all the way solving it. Another term is called eigenspace. So what is eigenspace? The set of all eigenvectors that satisfy ax equal to lambda x is called the eigenspace of A corresponds to lambda. So if I have a lambda and I solve this equation, A minus lambda I x equal to 0, it has non-trivial solution. It must have non-trivial solutions. So those non-trivial solutions are eigenvectors. If I group them all together, there are lots of them. It becomes a subspace, and we call it an eigenspace. So you can see that it is a subspace because it is a span of some bases. Okay. For example 1. Someone tell me this A 2, 3, 5, 4 has a eigenvalues of -1. So find one eigenvector for lambda equal to -1. And later on, we will actually find the eigenspace. So let's see. So how can I find it? We say, well, we just solve this. Solve A minus lambda I x equal to 0. So because it's the first one, I'll just write it a little longer. So that means AX is equal to -1x, right? And I'm going to solve this. Solve for x. That means A minus -1I times x is equal to 0. Okay, it's actually plus, right? You plus ix on both sides. So actually, I would say ax equal to -1i x. So it becomes plus 1i. Let's just say the 1 here. So and then so to solve it, that means I'm going to solve 2, 3, 5, 4 plus 1. 1i is 1001. X equal to 0. Okay, so that means I'm going to solve 2 plus 2 plus 1 is 3, 3, 5, 5. X is equal to 0. So that means I'm going to solve this. How do I solve this? I would use the augmented matrix 3, 3, 0, 5, 5, 0. Okay, do RREF. I think I have the 3, 3, 0, 5, 5, 0. So if I RREF A, it become 1, 1, 0, 0, 0, 0. You can actually do it by hand. 1, 1, 0, 0, 0, 0. So what is this? What is one? So x1 is equal to negative x2, right? So this is a perfect. There is three variables, so that means there's non-trivial solution, and x2 equal to x2. So what is one eigenvector? So let x2 equal to 1. So x would equal to negative 1, 1. So that is one of it. And this would be the representative for the eigenspace, actually. So actually, the eigenspace, so they didn't ask for it, the eigenspace, EIG, eigenspace is equal to span of negative 1, 1. Because basically, this is negative 1, 1, x2, right? So that is equal to when x2 is equal to 1, that is equal to negative 1, 1. You can check if you multiply, maybe I'll check here. If I multiply 2, 3, 5, 4, negative 1, 1, what do I get? 2 times negative 1 is negative, 2 times negative 1 is negative 2 plus 3, 5, negative 5 plus 4 is equal to 1, negative 1, which is 1 times 1, negative 1, right? Negative 1 times negative 1, so lambda is negative 1. And this is a eigenvector. And there's more of that because it's actually a space. So it is a span of negative 1, 1. So I'm going to do more example in the second page, but we will do it in the second video.